Welcome back to the Deep Dive, where we tear through the research and give you the knowledge you need without the slog.
Today, we're really getting into the engine room of programming.
Yeah, we're moving way past just dealing with one variable at a time. We're talking about data volume, how to manage huge numbers of values, all of the same type, but under one single name.
And that brings us to our focus for today's deep dive. The C array, the absolute foundation.
The origin point.
Exactly. Now, we should say modern C++ gives you much safer, easier tools. Things like std.array or the super flexible std.vector.
Right, from the standard template library. And for most things, you should probably use those.
You should. But if you really want to understand why those tools even exist, or if you ever have to work with older code,
Or high-performance systems.
right, where every single byte counts,
No.
then you have to understand the C array. It's
Yeah.
the most primitive and often the fastest way to group data.
So we're getting under the hood today.
We are. We're going to unpack the memory differences between static and dynamic arrays, look at their connection to pointers, their surprising limitations, and a really, really dangerous security flaw.
The buffer overflow.
The buffer overflow.
And I think the big idea for you to keep in mind here is that the C array is powerful because it's simple. But that simplicity, it demands absolute rigor from you, the programmer.
That's the core insight. It's the price you pay for all that efficiency.
Okay, so let's start with memory, because where the data lives really dictates everything else.
It does. And you've got two main types of C arrays, and the whole difference is about when the program figures out the size.
Let's start with a static array.
The static array is, well, it's rigid. Its size has to be determined and fixed when the program is being compiled.
So at compile time.
Exactly, at compile time.
Yeah.
And because the compiler knows the size ahead of time, a local static array gets put on the stack.
And for someone learning, why is the stack important? What does that get us?
The stack is incredibly efficient memory. Allocation, deallocation, it's all managed automatically, super fast. It's like a stack of plates, Last one on is the first one off.
But there's a catch.
There's always a catch. The speed costs you flexibility, the size is fixed, and the stack itself is relatively small. The size has to be a positive number, a literal, that you put right in the code. No changing your mind after you hit compile.
Okay, so if I need that flexibility, say I'm asking a user how many records they want to store after the program's already running, a static array is useless,
Completely useless. For that, you need the dynamic array.
a flexible one.
That's the one. Its size is determined during runtime, so it can be based on a variable, on user input, whatever you need.
And since the stack can't handle that kind of unknown, it has to go somewhere else.
It goes on the heap. The heap is a much larger, more flexible segment of memory.
But allocating on the heap means you have to use a pointer and the new operator, right? So we lose that automatic memory management.
You've hit on the exact trade-off. You, the programmer, you just became the memory manager. You're the garbage collector now.
And so while the array size is fixed once you create it,
The memory itself doesn't just disappear when you're done. If you don't manually free up that space with the delete command, you create a memory leak.
and I think people sometimes hear memory leak and it sounds kind of abstract. What's the real consequence?
In the real world, it degrades performance. A long-running application, like a server, if it keeps leaking memory.
It just eats up all the available RAM.
Exactly. It slows down, it becomes unstable, and eventually it can crash the application or even the whole system. That C array efficiency is tied directly to you remembering to use delete.
That's a perfect lead into our next section.
Yeah.
Because beyond memory, what really strikes me is just how primitive these arrays are. They feel unfinished.
They feel unfinished because the C philosophy is all about speed. Raw efficiency over everything else.
So no safety features.
No safety features. Adding built-in checks and functions would add overhead, and the language designers just said no, they are bare metal. So C arrays come with almost zero useful member functions.
Okay, so what are the biggest drawbacks then? What are we missing that we just take for granted in other languages?
Well, for starters, just finding out how big the array is, that's your job.
There's no size.
Louses. The compiler knows the size of a static array for a second, but that information gets thrown away as soon as you pass the array to a function.
And that leads right into the lack of aggregate operation.
Yes. You can't operate on the array as a whole. You can't just say array B and expect it to copy.
Or print the whole thing with one command.
Nope. Everything. Input, output, comparisons. It all has to be done one element at a time, manually, in a loop.
That sounds like a lot of work, and it sets up the infamous shallow copy trap. Walk us through that.
Okay, so remember, a dynamic array is just a pointer to some memory on the heap.
Yeah.
So when you try to use the assignment operator, like array B equals array A, all you're doing is copying that memory address.
The pointer.
You're just copying the pointer. You haven't copied a single piece of the actual data. You've just made two names that point to the exact same block of memory. They're aliases.
So if I change an element using array B,
Then array sees that change instantly because they're looking at the same data. That's a shallow copy.
and a deep copy, a real independent copy.
You have to write the code yourself. You have to create a brand new dynamic array, make sure it's big enough, and then loop through the original, copying every single element over one by one.
That manual rigor again.
It's the cost of working at this low level.
This link between the array name and its memory address is so important. Is the array name literally just a pointer?
It's a subtle distinction, but a good question. The name itself isn't a variable pointer you can change. It's a constant reference. But C++ has this thing called array decay.
Array decay.
Yeah. Whenever you use an array, like passing it to a function, it automatically decays into a simple pointer to its very first element.
So the array structure itself kind of dissolves and you're just left with the starting address.
That's a great way to think about it, and that's why arrays are always passed to functions using pass by reference. The system only ever passes that address.
Which is super efficient. You don't want to copy a million elements every time you call a function.
Efficiency is everything.
Yeah.
But that same decay means you can't, for example, return a local static array from a function. There's no operator to handle that whole block of data.
Now, what about dynamic arrays? You said returning one is a really bad idea. Why is that so problematic?
It creates an ownership crisis. I
Okay.
mean, if you create an array on the heap inside a function with new, that function now owns it. It's responsible for deleting it.
Only if you return the pointer.
You've handed that responsibility to whatever called the function. And if the caller doesn't know or just forgets to call delete on what it gets back.
You have a guaranteed memory leak.
A guaranteed systemic memory leak. And those bugs are a nightmare to find because the crash might not happen for hours.
It's why the best practice is to pass an empty array into the function and just have the function fill it up.
So this theme continues. The programmer has all the power and all the responsibility. Let's shift to a specific type of array where this has led to, well, catastrophic results. The C string.
The C string. The original way to handle text, it's just an array of characters with one non-negotiable rule.
The NUL character.
It has to end with the NUL character, 0. That little marker is the only way C++ knows where the string actually stops.
And dealing with text, especially from a user, is where a massive security flaw comes into play.
A massive one. A C string is often just called a buffer. And even though we just said C arrays don't have aggregate operations, C strings are the big exception. The SYN function lets you read a whole line of text right into that buffer.
But it doesn't check if the text will actually fit, does it? It often doesn't. And that is the birth of the buffer overflow. If you make a buffer for 100 characters and the user types in 150,
those extra 50 characters have to go somewhere.
and they do, the program just keeps writing them sequentially into memory right past the end of your buffer. It walks right out of its lane.
And just overwrites whatever was sitting next door in memory.
It gets corrupted. And our sources all agree this is one of the most dangerous security flaws in history because what's next door isn't just random junk. It's often critical program information.
Like what to do next.
Exactly. A clever attacker can craft their input, those 150 characters, so that they overwrite the return address of the function.
So instead of the program going back to where it came from,
It gets redirected. The attacker makes a jump to their own malicious code, which they've sneakily hidden inside the buffer itself. It gives them complete control of the program and maybe the whole computer.
that's terrifying. It compromises everything. Confidentiality, integrity, availability.
It's the ultimate lesson. The raw speed of the C array is a powerful tool, but when you combine it with a failure to manually check boundaries, it becomes a security nightmare.
A phenomenal insight. Okay, let's move from vulnerabilities to utility. The most fundamental use for an array is just managing and ordering data. Sorting.
Sorting is a core operation for so many things, databases, search algorithms, you name it. And the first step for almost any fast sorting algorithm is you have to get all the data into memory first.
Usually in an array.
Almost always in an array. And if you have your data in a C array, you've basically got two ways to sort it.
The smart way and the
Yeah.
student way.
Student way, exactly. Let's start with the smart way. In the real world, you use a library. The algorithm header in C++ has a sort function that is incredibly optimized, fast, and tested. You just use that.
And then there's bubble sort.
Bubble sort. Every student's first sorting algorithm. It's simple, I'll give it that. You just repeatedly step through the list, compare adjacent elements, and swap them if they're in the wrong order.
The big numbers bubble to the top. Easy to visualize.
But the performance is awful. I mean, truly terrible.
Mhm.
Because it's constantly comparing every single pair over and over. It just does not scale well. It's one of the worst performing sorting algorithms there is.
So why do we even teach it?
It's a teaching tool. It's like learning to use a hand crank to start a car. It shows you the mechanics of how a comparison and a swap works, which is a useful concept. But you would never, ever use it in a real program of any significant size.
Okay, let's expand our view one last time. Data isn't always a single line. Sometimes it's a grid or a table.
Right. Which brings us to two-dimensional arrays. They're incredibly useful for modeling anything with rows and columns. A spreadsheet, a game board, a map.
Like tic-tac-toe.
Tic-tac-toe is a perfect example. And even though we think of it as a grid, it's important to remember that in the computer's memory, it's still just one continuous block of data.
It's stored linearly.
Stored linearly in what's called row major order. The entire first row is stored, then the entire second row is stored right after it, and so on.
And the sources mentioned this can go even further into 3D arrays for things like video game graphics.
Exactly. And all the same rules apply. Static versus dynamic, the pointer relationship, the need for you to manage the memory, it all scales up to these more complex structures.
Fantastic. This has been a true deep dive, from the stack all the way to catastrophic security flaws.
So to recap the key points, C arrays are essential for handling lots of data. Static arrays are fast and live on the stack, but they're rigid. Dynamic arrays are flexible and live on the heap, but you have to be the garbage collector and call delete.
And we learned that array names decay into pointers, which explains both their efficiency and the danger of the shallow copy trap.
And the central lesson just keeps coming back. The simplicity of the C array is its power, but it's an unforgiving power. Every forgotten memory deallocation, every unchecked boundary is a bug just waiting to happen.
It's the ultimate expression of C's philosophy. Trust the programmer.
For better or for worse.
Now, for our final provocative thought for you to mull over. We talked about why returning a dynamically allocated array from a function is such a bad practice because of ownership and memory management. We want you to research the specifics. When that pointer to the dynamic array leaves the function, the pointer variable itself is destroyed. So what happens to that block of memory it was pointing to out on the heap? Why does that specific situation lead to such notorious, hard-to-debug instability in applications?
Until next time, keep digging deeper into the hidden costs of code efficiency.